So the first one, these are going to be straightforward. These will be, I'm going to have the same answer choices. Maybe I'll throw in another distractor or two just to distract you, but you're going to have these descriptions and you're going to have those choices mixed up in a different order, maybe some other choices too. So an oscillation in matter, and any oscillation, that could be any kind of a wave. It's an oscillation that sort of travels through space, transfers energy through space, but the fact that it's in matter, that means it's a mechanical wave. So this is A. If it's an oscillation of a magnetic field and an electric field, that is an electromagnetic wave. So really, there are two big classes of waves that I know of. There's the kind that go through air or go through water or go through this desk, and that sends vibrations through some substance. Those are all mechanical waves because they're in matter. But even if you don't have matter, in empty space, these waves can travel. That's why we can see the moon and we can see the sun, and sunlight can get to the earth. There's nothing in between us for the waves to travel through. If the sun blew up right now, huge explosion, could we hear it? Well, the answer, technically we couldn't hear it because hearing requires sound. So if this is the sun, I'll just draw it as a star like that. You have to have waves traveling through the air or through water or through some kind of material, and there's nothing out here. There's nothing for sound waves to travel through. So you can't have changes in air pressure between the sun and the earth because there is no air. So if you go to the moon, you can't talk to anybody with sound. Even if you could survive without a spacesuit on, there's no sound because there's no matter for mechanical waves to travel through, like sound waves. But you can see light. Light is a little different. Light can travel through empty space. It doesn't require matter. All right, enough of that. Oscillations parallel to the direction of travel. What that means, that's this kind of a wave, where if I draw a slinky, you compress this part, and then that bounces back and it compresses the next part, and that compresses the next part. And you do that by pushing like this and then pulling like that. You push and pull, and the wave goes this way, parallel to the way you pushed and pulled. And that's called a longitudinal wave. So that's C. Yeah. I think so. If you look in the top left individual cubby there should be a packet. No, down. The little small cubby. Up one. Is there one there? If there's not, I can print you one later. So the number 3, oscillations perpendicular to travel. What that means is you shake a rope like this, and the wave goes this way. These are perpendicular. So this kind of wave, this is the kind where the oscillation's up and down, the travel's this way. That's a transverse wave, so that's B. And then finally, an oscillation that can travel through a vacuum or empty space. This is like light traveling from the sun to the earth. The only kind of thing that can do that is an electromagnetic wave because it doesn't need matter to travel through. Couldn't find one? Okay, I'll hunt one up for you in a little while. Which of the following is not a property of all waves? So they transfer energy. That's true. Right now I'm transferring energy to you. You're feeling with your ears the energy I'm sending to you. Light is energy. It heats up the earth. So all waves transfer energy. Oscillations, yes, that's what makes a wave wavy. It's the back and forth part. They travel from one point to another. That's true. The waves travel. If it just sat in one place, it would just be a thing pulsing. And finally, can travel through vacuum of space? No. Some can, but not all. So the only kind that can do this is these electromagnetic waves. Mechanical waves can't do it. So this one's the one that's not a property of all waves. So I don't know exactly how I'll phrase this. I may have a couple of questions asking you which one is a property of all waves, and you would have to choose one of these other 3. I may just give you the same exact question, scrambled up, and I may pick some other thing that's not a property of all waves. I don't know. It won't be this exact question, but you need to know that all 3 of these are properties and that is not. or that's only a property of electromagnetic. All right, match the abbreviations. This is the symbol for wavelength. So that's lambda. Lambda is the symbol for wavelength. Some of these are symbols, some of these are units. Big T, that's a symbol for period. I don't know of a good way to remember that. I guess it's like time period, but it's a big T. So that's C. S is just seconds. I think people try to stay away from it as a unit because it's seconds and it's a unit we use a lot. So the only thing up here that's measured in seconds is period. Period is if you have something that's shaking back and forth. It shakes up, shakes down, shakes up, shakes down. A period is the amount of time for it to go up and down and back again. So if you look at a wave and you imagine somebody swimming in the ocean here in these waves, if this person experiences one period, that's the amount of time to be from here to go up and then back down to here again. So you can sort of visualize it as one wavelength, the amount of time for this whole wave to travel from this point to that point. So however many seconds that is, that's the amount of time it takes them to go through a full period, full cycle. So C, periods is seconds. Hertz, this should be a capital because the person who it's named after is a person. So it should be a capital H, not a little h. And that's the unit for frequency. Hertz is cycles per second. So if I say something in a high voice, like that, that's my vocal cords vibrating back and forth really fast at very many hertz. And then if I go, that's my vocal cords vibrating back and forth more slowly with a lower number of hertz. Meters per second, this is a unit, and the only thing that it matches with is wave speed. This tells us how fast something goes. So that's the speed of a wave. Meters, that tells you how long something is. In distance, period is the length in time, but wavelength is the only thing up here that's a distance. So that's D. And then finally, V is the symbol for velocity, and the only one of these that's a velocity is wave speed. So that's B. All right, now, so expect something like that. It's going to be pretty much these same things scrambled around in a different order. Just be able to match them up. I don't think I'll even put in any other distracting choices. I might, but I'll at least have those four. Darken the approximate period and frequency of the wave on the right. So again, I like to draw a little person here just so I can imagine somebody at the beach. And what period would mean would be how long it takes for them to be, the amount of time between splashes. So they get splashed, how long does it take before they get splashed again? That's the period. You can also just find one full wavelength on here, and that'll give you the period. So from here, the easiest way to measure a wavelength for me on this is to go from this point to that point. That's a full wavelength. That's equilibrium position, heading down, heading back up, heading back down, passing through equilibrium position again. And this is time 0, this is time 13, so the time is 13 seconds for the period. That's how long the wave would last. That's how long it would take between splashes for the person. And then frequency. Frequency is just 1 over period. So if the period is 13, then the frequency is 1/13. So it's that. And that formula is up here. Period's 1 over frequency, frequency is 1 over period. Okay. Number 13, wavelength. Which one has the longest wavelength? So this is a irritating jumble of waves, but I think you can pick it out pretty quickly. This is the one with the longest wavelength. You just have to look at one full cycle, and this goes through a full cycle from here. As it's at equilibrium, it's at 0, it's going uphill. And the next time it's at 0 going uphill is right there. So that's the longest one. That's 2 meters. So that is, that's letter D. What is that wavelength? Well, 2 meters. Which one has the smallest amplitude? Amplitude, when a wave is going like this, amplitude is this distance. Let me draw it bigger. It's not the distance from a crest down to the trough, it's half that. It's the distance from there to there, or the distance from here to here. So I'm looking for the smallest amplitude. That would be the shortest wave from top to bottom, which is this one. So that's A. And what is that in meters? I just need to go to equilibrium position and find this distance, and that's 0.1. Which two waves, when added together, always produce constructive interference? So this one may change. I may ask you about destructive interference. So be expecting either kind of question on the quiz. Constructive interference is when the two waves add to one another all the time. Like one's positive and the other's positive, and the sum of those is bigger. Destructive would be the opposite. So the two waves that are in step with one another are this one and this one, because this is biggest when this is biggest, and this is most negative when this is most negative. So if you add these two together, you're going to get this negative thing plus that negative thing. You get a wave that's really negative here. And if you added this together, this would be this much positive plus that much positive. You get a wave that's really positive. So those are the ones that are doing constructive interference, always. Right here, they're both 0. Neither one is, I mean, they're kind of adding together, but they're definitely not subtracting. So the answer is, what's that one? B and C. Now if I had asked you which ones are doing destructive interference, I don't think there are any. I don't see any that are totally out of step with one another. This one and this one are kind of out of step, but not exactly. This point doesn't line up with that point. If they did, if this was right above that, then this would be destructive interference. They've got to have the same wavelength for that. This and this, they've got the same wavelength. That's how they can have always constructive interference. This is maybe one of the hardest ones. If you got this right, pat yourself on the back. How many beats can you see? A beat is when you put two waves together that have similar wavelengths and similar frequencies, but not exactly the same, and you hear you hear a louder, softer sound. And here I'm going to find one beat. One beat is right about here. And let's see if there are any other beats. Yeah, right about there. So the beats are when these two things match up and they're together. So if I add these two things together, you're going to get an extra big wave right here and an extra big wave right here. Same thing here and same thing here. So it's going to be, these two places are going to be loud. Those are the beats. So there are two of them. And in between, you didn't have to label these, but this would be really quiet. That's just between the beat. And also right here, because this is positive when that's negative, they're going to add up to 0. So those quiet, loud, you hear two beats. Almost done. This is what longitudinal waves or sound waves really look like. So if these were sound waves, this would be high pressure. This would be the air going up above 14.7 psi, and then this would be low pressure, the air dropping down below 14.7 psi. And it's just, we don't usually draw them like this because you can't graph this very well. You can make a nice graph of something like this, but you can't for this. So the loudest sound is the one with the highest pressure. This is the quietest sound. This is medium. This is the highest pressure. They're most pressed together. So that's the loudest. Least amplitude, that's really the opposite of what I just did. Amplitude, so high, I'm going to write highest, let me label it over here. Highest pressure equals most amplitude equals loudest. So this is the loudest sound, this would be the quietest sound, and this would be right in the middle. And you can tell by how compressed these things are and how high the pressure gets. So least amplitude would be B, because this is most spread out. And for for a rarefaction for the spread out part, this is least spread out. So with the loudest sounds, the rarefactions are the most spread out. The pressure is really low here, and the compressions are really close together. Pressure is really high. For a quiet sound, the compression's not as close together, and the rarefactions are not as spread out. So this pressure isn't as high, and this pressure isn't as low. If you had no sound at all, what would that look like? It would look like this. The air pressure would just be the same all the time, and you wouldn't hear anything. All right, so last, the period of the wave shown in answer choice B. So with the sound wave, with a transverse wave, you find the period by measuring the time of one wavelength. So however many seconds that is, then that gives you the period. For this, you do the same thing. So the wavelength for this is from here to there. That's one full cycle. The wavelength for this one is from here to here. That's one full cycle. And the wavelength of this one is from there to there. That's one full cycle. I'm picking one part and then going to the same kind of part. Answer choice B, though, here to here, looks like this is 8 seconds, and this is 19 seconds. Here, let me erase that so I can see really well. That's not 19 seconds. This is 16 seconds. This is 8 seconds. So 16 minus 8 is 8. That's it. So you're going to have 21 questions on the quiz, just like 21 questions here. Does anybody have any questions about this?